Hello again. We are going to continue from the point where we have left, and we have just mentioned about playing around with the model in order to obtain a much more simplified and comprehensible model. And some of these tricks were helping us to create a standard form for the linear programming model so we can solve it through the simplex algorithm. Now we are going to do something much more complicated, and we are going to convert a constrained problem to the unconstrained problem. Now you may think that if this is possible, then we can solve every problem as unconstrained problems. However, obviously, we cannot always state that the unconstrained problem that we are going to create here will exactly give the optimal solution of the original problem. However, it is going to give us some information about the optimal solution or the optimal objective value of that problem. Now, let's just say we have a generalized mathematical model which uses a vector of decision variables x. That bold x here is a vector of decision variables of dimension n, and the objective function uses all of these decision variables and convert them into a real value which is supposed to be minimized. So our objective function is to minimize the f value, f function of the decision variables. Now, we may have a different type of constraints, but if we have greater than or equal to type of constraints, obviously they can be written in the form of a less than or equal to by multiplying both sides of the inequality with -1, as we have learned earlier. So actually we can generalize this as we have either have less than or equal to type of constraints or equation type of constraints. So let's just say we have a sequence of functions again, which are using the same set of decision variables as inputs. We have all of these m functions from g1 to gm of the decision variables, and the function values are going to be less than or equal to 0. These are the inequality type of constraints. And again, we have another sequence of functions from 1 to p, which are represented by index j. At j of the decision variables, this time they are all going to be equal to 0. Now, you may say that why we are forcing the right-hand side as 0 if we are talking about a general model here. Now, consider that all right-hand side values are taken on the left-hand side and subtracted. If they are positive, they are subtracted from the left-hand side of value. So they are also contained in the functions gi and hj. Therefore, the right-hand sides are equal to 0 in general. And again, we are not forcing the variables to be non-negative or non-positive, or we are not telling also they are unrestricted. We are simply saying that these vector of decision variables are in a set S. This S can be a type of polytope set, which is basically intersection of half spaces. Or simply we can say that they are combinatorial, so they are basically discrete, a set of discrete points. All right, so we have such a constraint model. We have inequality type of constraints in the form of less than or equal to and equation type of constraints. Now, it is possible that we can remove all of these inequality and equation type of constraints from the model and keep only the constraint which gives us the acceptable, feasible solution space for the variables only, okay, here. And we are basically rewriting the objective function as the previous objective function plus an alpha function of the decision variables, and we call this new objective value or objective function as fk of x. So alpha x here is added by the removal of the constraints here, two sets of constraints. In total, there are n plus p constraints here, which are all removed, and we have introduced a function in the objective value. Now, this function will be called the penalty function, alpha of the decision variables, And how we are going to write this penalty function is explained here. Now, let's focus on this equation. First of all, we have two summations. In the first summations, the summation is run through the index I. I is changing from 1 to n. So this means for each of the inequality type of constraints here, we are adding up components calculated in the summation. And what are these components? First of all, we are saying that all of these GIX values on the left-hand side of the constraint are supposed to be negative or non-positive, let's just say. So whenever these constraints are violated, or whenever GIX, any GIX value is positive, then we are going to maximize that value with 0. Obviously, the positive value is going to be maximum. So we are going to look at the maximum of these two values. And we are going to take the kth power of this maximum and multiply it with a penalty function mu I, or I'm sorry, penalty value with mu I, which is going to be simply relatively large number. Now, if the constraint is satisfied by an assignment of the decision variables, and then that constraint is going to be, the left-hand side of that constraint is going to be negative, and the maximum of 0 and the negative value will simply be 0, and the kth power of 0 will still be 0. Therefore, the penalty is going to be evaluated as 0, even though this coefficient mu I is large, relatively large. It doesn't matter, because when you multiply it with 0, it will vanish. Now, we are especially selecting a k value which is a positive integer. So the least possible value for k is 1, but we can choose 2 or 3 or 4 here. So this means whenever you violate the constraint, the ith constraint here, whenever the left-hand side is greater than 0, its kth power is going to be even greater. And when it is multiplied with the coefficient mu I, which is a relatively large number, it is going to be greater, which means it is going to contribute a lot more than the original objective value f here to the new objective function. However, when the constraint is satisfied, there will be no problem. So this is just going to occur or happen for all components from 1 to n. For all inequality form of constraints, we are going to multiply the violation amounts, or take the power, kth power of the violation amounts, and multiply them with the relatively large number mu I, and write this as a penalty function. Now, a similar situation should also be written for the second set of constraints as well. Now, whenever the left-hand side is different than the right-hand side, these constraints will be violated. Therefore, the absolute value of HJX values will represent the violation amount. So whether negative or positive, it doesn't matter. When we take the absolute value of that function, it is going to be a violation amount of the constraint. Again, we are taking the kth power of this violation amount in absolute value. Of course, if k is 2, for example, it's an even number. In that case, the absolute value will not be a necessary thing to write. However, you can also take other integer values such as 1 or 3. Therefore, the violation should also be measured positively. Now, kth power of the violation amount for an equation type of constraint will also be multiplied with another coefficient mu j. For each function, we can define mu j differently. So depending on which constraints are important for us to satisfy and which constraints are softer constraints, we can define different type of penalty parameters here. And again, for all equation type of constraints, when we take the k power of the absolute value of the left-hand side and multiply them with the relatively large coefficient, we are again introducing a penalty to the new objective value on the right-hand side. So basically, what we are doing here is, instead of writing the constraints as hard constraints in this problem, we are softening them and introducing them as penalty functions in our objective function. However, because we can select arbitrarily large k values, for example, you can select k as 4 or 6 or 8. You can select an arbitrarily large integer for k value and arbitrarily large coefficient here. Comparatively, the contribution of a violated constraint on the left-hand side to the objective function on the right-hand side is going to be a lot larger than the contribution of f, the original objective function, in the new objective function. Therefore, in the right model here, even though the constraints are not forced to be satisfied, previously listed constraints are not forced to be satisfied, they are simply going to create a huge amount of objective value. And if your intention is to minimize this new objective value, among the feasible solution set indicated by this final constraint is going to choose the x values, which is going to basically minimize the right part of the objective value. Okay, so the violation is going to be minimized. It is the main part that we are going to focus on rather than minimizing the objective value. Obviously, not all constraints in the original model will be satisfied here. Maybe some of them will not be satisfied in the right model, but this is a minimization problem, as you can see, and we know that because these constraints on the left-hand side are relaxed and removed from the feasible solution space, the new feasible solution space is going to be expanded. Therefore, the minimum value in this new space is going to be better than the actually for fx value is going to be less than the minimum value of the model obtained on the left-hand side. However, because the penalty functions are significantly contributing whenever a violation occurs, we can also define a boundary by the objective value in the optimal solution on the right-hand side to the model on the left. Okay, so basically, instead of solving the problem with a constraint optimization procedure, we are basically removing these constraints and defining a nonlinear maybe or a linear. Of course, it is possible to define somehow a linear function or convert these functions into linear functions to the objective function here. And well, actually, when you are converting them to a linear objective function, or maybe you are going to get the original model in any way. So basically, we are trying to minimize a much complex objective value. However, in an unconstrained space, we are basically transforming our problem from a constraint to an unconstrained problem. Now, not every time you are going to be able to get the optimal solution of the original problem. However, there are some cases, for example, if all of these functions, f, gi, and hj, are linear functions, we call such a practice with a Lagrangian relaxation procedure when the k values are equal to 1 and the coefficients are flexibly determined in the optimization procedure. And Lagrangian relaxations sometimes help us to find the objective value of the original problem exactly. For further applications of the Lagrangian relaxation, I recommend you to check the Wikipedia page. Lagrangian relaxation is going to be used as a solution procedure for these kind of problems. And remember now, our objective is not to apply a solution procedure or learn solution procedure in this class. We are just interested in the different type of mathematical modeling approaches and how we can play around with the models here. It is possible, as we can say here, it is possible to transform a constraint problem into an unconstrained problem, though the optimal solution of the new problem will not be the same as the original problem. There are some cases where either they are close to each other or in the objective value they are close to each other. And there are some cases, just like in the LP applications, it is possible to exactly get the optimal solution of the original problem. Now let's see how we can transform a nonlinear mathematical programming model or nonlinear programming model from a constrained model to an unconstrained model by using the understanding that we have learned in the previous page. So our model is this. We have two decision variables, x1 and x2. The objective value is x1 minus 3 to the power 4 plus x1 minus 3x2 to the power 2, and we are trying to minimize this summation. So we have a polynomial type of objective function here, and obviously this is a multimodal objective function. I mean, as far as I can imagine it, there may be multiple modes, maximum and minimum values for this kind of polynomial. Obviously, if you want to see it, really, you need to check the derivatives and solve them for 0. Or you can simply use a software to draw such a function to see if the maximum or minimum value occurs at which points, local minimum points. Now, we have two constraints here. Basically, in the previous general application or general explanation, we were having two sets of constraints. Again, we have two sets of constraints here, but in each set, we only have a single constraint. As a less than or equal to type of constraint, we have 3x1 square minus x2 to be less than or equal to 30. And as an equation type of constraint, we are forcing x1 square minus 3x2 to be equal to 10 exactly. And x1 and x2 are unrestricted variables. We can choose any combination of real numbers here, either negative or positive. However, the constraints here should be satisfied. Now, we are going to convert this mathematical model, nonlinear mathematical model. It is nonlinear in every way because constraints and the objective function, they are all nonlinear. We are going to remove these two constraints from the constraint set, and we are going to add them as a contribution to the objective function. The first contribution will be the difference between the left-hand side and the right-hand side of 30. First constraint, I am sorry. So we are going to take the difference between the left-hand side and the right-hand side. If this difference is positive, my friends, this means this inequality is violated. It is not satisfied. And we are going to compare this difference with 0. If it is positive, then there is a contribution to the objective function. There's a violation of the constraint. However, if it is negative, if the difference is negative, then there is no violation of the constraints. It is satisfied. Therefore, no penalty should be contributed to the objective value. So we are taking the maximum of 0 and this difference. There is a special name for this value, actually, the positive part of the difference, we say. So when you take the difference of the left-hand side and the right-hand side here, if it is positive, you take the difference, but if it is negative, you take it as 0 in this comparison. This is also called the positive part of the difference. Now you take the second power of this positive part, simply squaring it, and multiply it with a, again, penalty coefficient, mu1, which is comparatively large number to the ones that we are seeing in the objective value. And this is the first contribution as a penalty in the case of violation of the first constraint. Now, for the second constraint, we are forcing this left-hand side to be exactly equal to 10. So when we subtract the right-hand side from the left, we expect it to be equal to 0 in the objective, in the original mathematical model. However, this time, if we are going to introduce a penalty for the violation of this constraint, we are calculating the absolute difference between the left-hand side and the right-hand side of this constraint. And when you square the absolute difference here and multiply it with another coefficient, mu2, which is the penalty coefficient here, you get the second contribution for the violation of the second constraint in the original model. Then you transform the model as the minimization of the original objective function plus alpha 1 and alpha 2 of the decision variables, x1 and x2. Now they are going to create a penalty for the objective function in case of any violation of the previously mentioned constraints. However, because the penalties are going to be significantly large in case of any small amount of violation, the objective function will basically focus on to eliminate all of the contribution coming from the penalty functions and rather minimize the original objective function by satisfying the constraints here. So the only constraints that are left are basically the constraints that the decision variables should be real numbers. So again, it is up to the modeler or how you are going to choose mu1 and mu2 coefficients, penalty coefficients. Again, you can choose a different positive integer other than 2. Maybe you can choose 3 or 4, depending on how you would like to solve the problem. In the solution procedure, these kind of choices may or may not help you. Or, I mean, you need to choose a logical number, because when you choose these powers large, then the objective function will not be that smooth, and you are going to see huge amount of increases and decreases whenever a function constraint is violated or not violated. In this small size example, it is not going to be a big problem for the solution. However, for complex problems, converting a constraint problem into an unconstrained one requires some expertise in the definition of the powers of the violation and also the penalty coefficients of the penalty function.